the cloud. Okay, you guys heard me do it. And I'm going to go share screen and go to here. Okay, and move that to the bigger screen. Come on. There we go. You guys should see that by now. Thumbs up?
Yep, thumbs up.
Okay, great. Right, so today is the last day we're going to talk about design of materials and integrated computational materials engineering. So for those of you who are more mechanically oriented, today's probably a day of relief. And we're going to switch gears and we're going to talk about mechanical design and designing geometry to maximize the structural efficiency of a frame or a monocoque, or et cetera, so structure. So just kind of review a little bit. Where we left off last time is we talked about the structure property link in design for stiffness for materials, more specifically design for stiffness to density ratio. And we gave a simple example of how you can predict the stiffness of a material from the microstructure using composite materials and the law of mixtures. It's a simple example where you can look at a microstructure of a polymer matrix composite, for example, and you can look at the amount of fibers and you can look at the amount of matrix and calculate a volume fraction. And knowing the stiffness of each of those two different constituents, you can then calculate out the stiffness for the entire composite. So that is an example of where you're using a predictive model to get from structure to properties, in this case, stiffness. We also talked a little bit about this program called OOF, which was developed at NIST, which I used a long time ago as a graduate student. This is a software where you can actually take a microstructure that you might get off an optical microscope or a transmission electron microscope or TEM even, and then you can go ahead and apply a finite element mesh to different portions, or we can do the whole material, but you can apply the finite element mesh to the entire microstructure, and then you can sort of define sub areas that correspond to the microstructure with different properties. So this can be done both in 2D and 3D, and this is a way in which you can, knowing the stiffness of the different constituents within the material, like if you know that the Martensite weight has some stiffness and the Austenite has some stiffness, or whatever, or the aluminum precipitates, whatever, you can go ahead and use OOF to calculate out what the far field stiffness might be of this microstructure. So that is an example of where you use computers to calculate out the stiffness of a material at the bigger length scale by knowing the stiffness of little constituents at the small length scale. So this is going from microstructure to macro stiffness. And then, so that's kind of the end of filling in the links for strength and stiffness. And then we talked a little bit about this diagram right here. And this is a diagram which I think encapsulates, pretty much all the big concepts from ICME. And this shows, how you design a material going from the angstrom level all the way up to the macro level. It shows the tools, the computational tools that you would use to do that on the right side, right here. And then on the left side, it shows some of the instrumentation that you would use in order to make measurements at those different length scales. And, you might use X-ray diffraction at the atomic level. You might use SEM at the scanning electron microscopy at the micro level, and then at the sort of the macro level where you might look at a casting cross section, you could just get away with optical microscopy. That's LM here, light microscopy. Here's my cursor. Here it is. Okay. So we've talked before about these processing structure property systems diagrams, and I wanted to show you what the full strength version of these looks like. So this is a real processing structure property systems diagram that was created a while ago, maybe back in the early 2000s or late 90s, or maybe even the mid 90s, for a high strength, ultra high strength landing gear steel. And this material was developed in the Steel Research Group at Northwestern University. And a lot of this shouldn't actually probably be too intimidating to you guys, because you've pretty much seen all this already, but in a much more, I don't know, simplified version or friendly looking version, because I use diagrams instead of words. But going up the left side here are the different processing systems. So you go from having steel or iron ore, you refine that iron ore, you take the oxides out of it. Where's my cursor keep going there? You take the oxides out of it. You have to work it down into some type of useful shape, like maybe a billet or a or a sheet, forging maybe, and then you solution treat it. We've spoken many times here over the past couple of weeks about solution treating of steel, where you take a body center cubic steel at room temperature and you heat it up to FCC, face center cubic, or austenite at above about 800 degrees or 850 degrees Celsius, and then you quench it down to room temperature rapidly, and there's no time for the FCC structure to go back to BCC, so it forms what's called a BCT, body centered tetragonal, is one possibility, and that material is called martensite. Martensite is very strong, but can be brittle. You can then temper that martensite to coarsen it a little bit, and in some cases even strengthen the material through what's called secondary precipitation hardening. We talked a lot about precipitation hardening. And then you have a material that can be tough and strong. So these various processing systems or steps create different structures in the material. The first length scale is perhaps the down here, it's called, let's just say the matrix. We'll go to the top here, actually, matrix material. So the matrix material, if you went through this process I just described, would be a lath martensite. If it's a material that's highly alloyed, you would have different versions of carbides, like an M2C carbide, where the M is the metal. It strengthens the material above that of the martensite. And that's this right here. That's the strengthening dispersion. Okay, so this is the various M's that you could use: moly, chromium, tungsten, vanadium, niobium, and then there's certain ones you want to avoid. So this tempering, how you do this tempering step, and we've discussed this ad nauseum over the past couple of weeks. How you do this tempering step is going to determine how much martensite you get and how much of this precipitation hardening material you're going to get. And this is a link we've talked a lot about, how you really can engineer this link using programs like Thermocalc, by using Thermocalc to do things like predict the driving force for these different carbides and knowing which ones to avoid and which ones to promote, and then tailoring the composition of the material and the tempering time and the tempering temperature to make sure you don't get what you don't want, but you do get what you do want. So these carbides get these carbides and not those carbides. We talked about strengthening via the Hall-Petch relationship, where you minimize the grain size because the strength of this steel, for example, could be an aluminum as well, nickel. The strength goes inversely proportional with the square root of the grain size. That's called the Hall-Petch strengthening. Niobium, as I mentioned previously, is a very potent method to keep grain sizes small. And a lot of steels use niobium. A lot of steel manufacturers use niobium to make sure that the grain stays small, or the word they use is refine the grain size and keep it that way long enough to use the material before it gets too hot and maybe gross. But hopefully it doesn't get that too hot. We talked about an example there with aluminum and the housing, the motor housing. Austenite, sometimes when you quench from the solution temperature, there is not enough time for all of the material to transform to even martensite. And sometimes you get a little bit of austenite left over. And that austenite, in some cases, can be good, in some cases can be bad. In this example right here, for ultra high strength landing gear, the austenite is actually very important. The austenite, I don't want to get into too much detail about this, but the austenite can actually increase the toughness of the material. Because what happens is when you have a crack tip, for example, suppose you had a little fatigue crack growing in your piece of landing gear, right? And the little fatigue crack hits an austenite grain, and then the energy somehow causes that austenite, the energy associated with the crack tip and the deformation from the deforming of the material ahead of the crack tip, that causes the austenite to transform to martensite. And there's a little increase in volume as you go from austenite to martensite. And that little increase in volume can actually reduce the stress intensity of the crack tip, so-called shielding the crack tip. So you effectively end up with a tougher material. And then finally, there's this issue of the system. The grain boundaries is another system. The grain boundary chemistry needs to be engineered. There's a failure mechanism called hydrogen embrittlement, which I'm not sure if you guys have gotten into in some of your undergraduate classes, but hydrogen embrittlement is a rather nasty little problem. I've experienced it several times myself. This is where you have a material that is a high strength material. Typically, it has a yield strength over 1 gigapascal. And what happens is when you, for example, if you electroplate this material, you get a little bit of hydrogen that diffuses in because you're, electroplating. You're oftentimes dealing with an aqueous solution, or most of the time you're dealing with an aqueous solution. Electricity during the process turns the water that's in the plating solution to hydrogen and OH. The hydrogen diffuses into the material. It begins to accumulate at grain boundaries and then creates pressure until the material cracks without warning. I can tell you as an engineering consultant, I've had several projects where I've had customers who bought cheap bolts from a various company I won't mention. They bought cheap bolts, and then even though they said that they were safe to use, they weren't. They were hydrogen embrittled, and they broke in service and caused all kinds of problems, all kinds of mayhem. And this is maybe where Steve gets involved. Anyway, so here are the microstructural systems: matrix, strengthening dispersion, grain size, austenite dispersion, and then the grain boundaries. These are 5 systems. And I should point out that we've only talked about how the strength of the material or the properties of the material can be dictated by these different systems and which one are present and how good they are: small, big, widely dispersed, etc. Volume fraction, we've talked about those things, but we haven't really talked much about that there's actually can be interaction between systems as well, as there is, for example, in the austenite dispersion and the way the grain boundaries are engineered. So the next link we've discussed here is the link going from the structure to the properties. And then we draw these causal links between the different subsystems of the microstructure to these different properties, okay? And the properties of their own systems. So the property of strength, strength is a system, toughness, hydrogen resistance. The strength comes from the matrix material. The strength comes from the dispersion. The toughness comes from the matrix material, and so on. You can start drawing these links down the list here as you see the relationship between which of these microstructural systems is causing these different properties, which is resulting in these different properties. Okay, so so this is it. This is where I think the whole topic of integrated computational materials engineering comes together in this diagram. This is what I want you to take away from the lecture. This is what I want you to remember about ICME, these interconnected systems of processing structure properties. This paradigm of these 2 links. I've used this many times. It's gotten me out of a hole many times in materials problems and designing materials. I'm stuck in a hole right now with a client trying to design a high strength cast iron for a dredging pump. And I'm trying to figure out what's wrong with their material and why it's breaking. And it's always very comfortable to be able to go back to this paradigm of this systems approach of processing structure properties. And you'll have to read like crazy in order to understand how to populate the 2 links, but it does work eventually. Sometimes it takes time, but it does get you into where you're trying to go. And I'm almost there with this particular client of mine and his dredging pump. Any questions about this, guys? Okay, so finally, historical perspective. I'd like to mention Professor Greg Olson. I've mentioned him several times previously in the past couple of weeks. Professor Greg Olson, I think, is really considered one of the pioneers of integrated computational materials engineering. He called it design and materials back in the day, and then it became computational materials engineering, and then it became integrated computational materials engineering. So there's been several iterations of what you call this process. Professor Olson got his PhD and undergraduate degree at MIT from 1966 to 1974. He got his PhD under Morris Cohen. And I think Professor Eager has known him for a long time. I think even when he was an undergraduate. Is that correct, Tom? He's not still there. Okay. After he finished his PhD, he was a research associate at MIT. I think at that particular point in time, MIT was sort of pivoting their curriculum away from metallurgy and more towards biomaterials. At the same time, Northwestern University was pivoting towards metallurgy. So he decided to leave MIT and become a professor at Northwestern University. He was there for, 30 years? He was actually on my committee, my PhD committee, when I was a graduate student at Northwestern. And just recently, he has decided to come back to MIT. He came back, I think, officially January 2020, right before the pandemic hit. And he decided to come back because I guess there's a newfound interest in the material science department at MIT in metallurgy. So he's back, and he is the thermocalc professor of materials engineering. He also started a company called Questech when I was a graduate student at Northwestern. And Questech is a company that has commercialized this ICME process. And they've had several interesting customers. They produced the alloy, the aluminum alloy that is in the iWatch, the Apple Watch, I mean, and now whatever, I guess they use that same aluminum on their computers and their iPads. That's public knowledge, I can tell you that. So he is a member of the National Academy of Engineering. He's an ASM Gold Medal winner, TMS Fellow, but perhaps most importantly, he has a world-class taste in cars. This is Professor Olson here with his relatively newly bought Lotus Elise. I think he bought this in 2012 or so. And he has a long history with British sports cars, as it turns out. He has what's called a Lotus Elan, which is an incredible example of structural optimization. I think the car was built in the 60s, and I got a ride in it once when I was a grad student. Anyway, and then I guess with the success of Questech, he was able to buy himself this nice Lotus Elise here, and I think it's a lot of fun with it. Anyway, he has a class on computational materials engineering. Anything that I've taught you over the past several lectures, he can do much better than me. So if you're interested to learn more about computational materials engineering, I highly recommend you take his course. This morning, I was trying to look up the exact number of his course, but I couldn't find it. So I tried to pull up the course catalog, and I couldn't really get it to download. Maybe you guys know how to do this better than I do, but he does have a course. He's teaching it right now, but I'm sure he'll be teaching it next semester as well. So if you want to learn more about integrated computational materials engineering, I highly recommend you take his course because, like I said, anything I've taught you, he can teach you a lot better than I can. So anyway, I recommend that. Okay, that concludes the material side of this lightweighting and structural efficiency part of the course. And now we are going to shift gears, and we are going to talk about how do you design the geometry of a structure, of a bicycle frame, of a car body, of a crane, an airplane fuselage, whatever it might be. How do you design the geometry of that particular structure to maximize the structural efficiency? So minimize weight, maximize stiffness, maximize strength, fatigue resistance, etc. Okay, so we're shifting gears now. We're in section 4. So here's an interesting example I want to start with. We have here 2 bicycle frames. These are both made of steel. They're both made in Italy. The one on the left is a Colnago from the mid-70s, and the one on the right is a 2020 Cinelli. These materials, these bicycles are both made by steel made from a company called Columbus, which is an Italian company. Columbus has been, I think, at the forefront of bicycle steel technology, God, probably since the 50s or 60s or maybe even the 40s. Well, actually, I take that back, maybe even the 20s. They got their start actually making metal tubing for furniture, for German furniture, like the stuff that came out of the Bauhaus. Not important, but anyway. So the grain frame, the Colnago, is made from a steel. It's a chrome and molybdenum steel. It's a pretty close to 4130 steel. It's probably, well, okay, the yield strength of this material is about 800, or sorry, the ultimate strength of this material is about 800 megapascal. And this frame is put together using a technique that's been used since the dawn of cycling, I think. It's called tube and lug construction. So you start with a tube, and then you have a steel lug, kind of like a framework. I'll show you some more about this later. And then you sort of put tubes into it to join those tubes together, and then you braze the tubes together with a little bit of brass. You use brass because it's low temperature, and if your steel is precipitation hardened, for example, you don't want to heat it up because you might grow the precipitates, and then they wouldn't be as effective, and the material would go down in strength locally around that lug. So using brass and brazing at low temperature, or in some cases they use silver solder, you can minimize that the coarsening of those grains. And now we know all about that, so you guys know exactly what I'm talking about, right? Right. Okay. The thinnest section, the thinnest tube, the thinnest wall thickness of this frame is right about here in the middle of this tube here called the top tube. And the wall thickness here is about 600 microns, or 0.6 millimeters. This frame, I think, with the fork, weighs about 2 kilograms. Okay? 2 kilograms, 1975 technology. The white frame here, the Cinelli, looks heavier because the tubes are much bigger in diameter, but it's actually a very different animal. The alloy that's used in this material the steel alloy that's used in this frame is actually a much more sophisticated version of this material that they used in the 70s. It has niobium in there for refining the grains. It has chrome, moly, manganese, and nickel to use for creating the secondary hardening dispersion of fine precipitates. Okay, and the ultimate tensile strength of this material is about 1,250 megapascals, so significantly stronger than the Colnago. And if you go on Columbus's website, they have a description of some of these alloys, and it's interesting how it's written because it's been translated from Italian. Not that I speak Italian, but you can kind of tell that it doesn't quite sound right in English. It's interesting to listen to, but some of it is very, very brutish, and it says, we use niobium for this. And anyway, you should go by. It's interesting to look at. Anyway, this frame is actually TIG welded together, so higher temperature but more focused. And I guess they can get away with that because the intersection, the area of material that they're joining is larger because the tubes are larger in diameter. The thinnest point on this frame, again, is right here in the middle of the top tube. And the wall thickness here is about 350 microns. So significantly thinner than the material in the top tube right here. This frame, including the fork, weighs about 1.6 kilograms. So substantially lighter. So they're using a stronger material, but how do you take advantage of that stronger material? How do you make a structure that's lighter, knowing that you have a stronger material? And that's what we're going to talk about for a good chunk of the lecture the next several weeks. Okay, anyone have any questions about this example? I love looking at this example because I think, this is just amazing. Like the change in technology, the increase in know-how that's gone from 1975 to 2000, and what you can do, if you have the right materials and you understand how the geometry works. Okay, the first thing to know about when it comes to designing a structure is to know the modes of loading. There are structural members that are in tension. Okay, that's when you're sort of pulling on things, right? There's compression, pushing together. There's shear, and I like to break this up into single shear and double shear. Single shear is shown here. Double shear is shown here. It's sort of how many points you have contacting the material where you're going to shear it. And a lot of people mess this up, and they use single shear. It's all over the place, and there's things that break all the time because people put things in single shear. Double shear is a much stronger, structurally efficient, stiffer way to put something in shear. If you look at the control arms on how they're mounted to, or the suspension arms in your car, and see how they're mounted to the chassis, in some cases, some manufacturers screw this up. Chrysler messed this up a lot of times. They never had any failures, but there are certain ways that they do certain cradle structures where they use single shear, which I always would object to. And then there's, to be honest, like the way the steering is connected, the steering, control arms are connected on your car. They're almost always in single shear. They really only use this on racing cars where they put in double shear on the steering system, which always kind of surprised me. The next sort of maybe more complicated mode of loading is bending. Okay, bending can be 3-point bending, it can be 4-point bending, and then there's cantilever, and this is just bending the material. There's torsion, twisting things in torsion. There's some examples of that, like there's torsion springs on old Porsches that they loved using. I think Acura used them in the early Integras too. Buckling, so buckling is a local instability problem. You have a column that's under compression and maybe it's too thin and not stiff enough, and it sort of collapses and fails and creates a real mess. This is this, for example, is I once did a calculation on a glider that we were making out of composite material, and you've got the glider, and you've got the wings coming out, and you've got the back section with the tail there, and actually there's sort of a compression load there because of the way the thing's flying, and the stability of the rear portion of the fuselage, the propensity for it to buckle was always the limiting structural case. So buckling is very important. These modes of loading, guys, this is really fundamental. This is really fundamental to the efficiency of the structure. Is designing these tubes knowing what loading load they're under. So look at these, take a deep breath, remember them, always keep them in here, because people really tend to not focus on these things. They tend to overlook these things, and they can cause all kinds of problems. So know your modes of loading. Any questions? Okay. The stress, you can calculate the stress of a structural member, a beam or tube or whatever, using these equations here. So when you have a tube that's under tensile or compression, the load, the stress field, is sort of linear across the face. That means that as you go across, the material, the stress field is constant as you go across, right? And if you imagine these beams that I've drawn here having a dimension B that goes into the page, the stress is given by the load P divided by the cross-sectional area. Okay, that's nothing too brilliant. I'm sure you guys have seen that 30,000 times. But what's interesting to note here is that the stress goes down as the H goes up in a linear way. So you increase H and the stress goes down, but it goes down linearly. So if you increase the H by 2, the stress goes down by factor 2 as well. Okay, linear relationship with cross-section. Same would happen for B. The stress is inversely proportional to the cross-section, linear relationship. When you get to bending, things get more complicated because the stress is given by this equation here. The moment applied to your beam is M, and again, the stress field, the dimension going into the page here is B. I should probably fix these slides so it shows that. And then the width of the beam is H, and here things are very different. Okay, very different. The stress goes with the inverse of the cube power, the third power of the H. So this means that as you increase H, as this guy becomes wider, okay, in the plane of bending, that's a critical part of the plane of bending, the stress goes down very rapidly. So for the same bending moment, as you increase this H, the stress goes down really quickly. Torsion is similar. Torsion, move you guys over here. Torsion is the same thing, except it's even more pronounced. When you have a tube in torsion, and that tube has some radius r, the shear stress, because we're in tension now, or we're in torsion now, the shear stress goes down with the raised to the fourth power. Okay, that's a big deal. So that means that as you increase the radius of this guy, as you increase the radius of this tube, the stress goes down really quickly. Really quickly. And I'll try to, I'm not sure how good this slide is. I struggled with this slide in the past. So let's just, this slide in the past. So let's just try to go through this slowly so it makes sense. If you have 3 tubes, or three, these aren't hollow, 3 solid bars, thank you, bars of material, and they're all subject to the same torsion load. You've got a yellow one, you got a green one, you got a blue one. The diameter of these tubes, goes up. So the blue one has radius r, the green one has the radius divided by 2, and the yellow one's got the radius divided by 4. Okay, if you could draw this coordinate system here, where you've got radius going up and down, and you've got stress, shear stress, going this way. Okay, if you draw this guy, and you could draw what the stress looked like as a function of this radius, you see that the initial stress given some m is this tiny little, right here. You can show it in the blow up. It's this tiny little vector right here that would the magnitude of this, the length of this little line here would be the stress. As you half the diameter of this guy, okay, the stress would become this line right here. Okay, so the stress has gone from being this tiny little thing here that you can't even see to this length, this line here. The length of this line is proportional to the stress. Okay, now if you go to a quarter of the radius, the stress goes up to this yellow line here, right here, this yellow line right here. So as you've gone from a radius of r to r by 2 by r by 4, the stress goes up really, really, really quickly. See that? Another thing to know here is that the stress, when you have bending and when you have torsion, the stress is much higher as you go in bending, as you go away from the central axis, where the stress is 0, and all the way out to the far skins. So the further you go away from the center, the higher the stress gets until it hits a maximum on the complete outer boundaries of this beam in bending. Okay, so the stress is really high here, and it actually goes to 0 in the center. The stress, depending on the direction of bending, the stress is going to be compressive on one side, and tensile on the other side. But you see here, like I said, like the stress is really high on the outside and really small in the middle, which means that the material on the outside of this structural member is doing a hell of a lot more than the material in the center. The same thing is true for torsion, except it's even more pronounced because of this. Well, I take that back. It's still a linear relationship. If you put this little beam or little bar in torsion, and the stress in the center is about 0, and as you go out towards the outer face to the circumference, the stress is maximum at this outer surface. Okay, so 2 things here. One, the stress goes up for bending and compression. For bending and torsion, the stress goes up very rapidly with changes in geometry, and the stress is highest at the outer skins. Very important. Okay, this is a fortunate property of the world of nature that we can use this in a very effective way to reduce weight. And here's an example. Suppose you had 2 tubes, tube 1 and tube 2. These tubes are the same length, and they are subject to the same bending load M. But tube 1 is smaller in diameter and has a thicker wall than tube 2. Tube 2 is bigger in diameter than tube 1, but it has a much thinner wall thickness. Okay, and I've gone ahead and defined that over here. So if the diameter of the tube 1 is r, okay, the diameter of the tube 2 is 1.4 times r, okay, and the wall thickness is half in this case. So in going from tube 1 to tube 2 and using these dimensions that I just showed you here, where the wall thickness is reduced by a factor of 2 and the diameter is increased by a factor of 1.4, these tubes actually have the same stiffness, or I'm sorry, the same stiffness. What did I do? Did I do stiffness or strength? Okay, sorry, the same stiffness. Okay, they have the same stiffness. These 2 tubes have the same stiffness, except tube 2 is about 2/3 the weight. If it's the same length, tube 2 is about 2/3 the weight of tube 1. Okay, so so this is great. By using this relationship, between bending and stress, we can create a tube that's lighter at the same stiffness, okay? Or conversely, we can make the diameter maybe a little bit bigger, the wall thickness a little bigger, and we can make an even stiffer tube that still could be lighter or be the same weight between the two. So this is a very powerful tool to use to create stiffer, stronger structures at the same time reducing weight. And that's exactly what these guys did. Okay, so these tubes are smaller and thicker walled. These tubes are bigger in diameter and thinner walled. This is actually a lot stiffer and weighs less than this one. So that's the structural efficiency science in action, let's call it, okay? It's, I actually have a bike very similar to this one from 1981, and I have a bike like this from 1996. And it's interesting because you pick the two up and this one actually really does feel lighter. You can really feel the difference. Okay, so in using these equations and using this approach where you're using different structural members of different diameters or different density materials, for example, and then setting the equations for each of those two equal. And if we were in class, I would derive this on the chalkboard like I do every semester. You can begin to draw these, what I call constitutive relationships of weight savings. And they're shown here. There are these material, mass of the second one versus mass of the first one is a function of the two densities, the density of the first one, the density of the second one, so the material density, and then the yield strength of the material, or the stiffness of the material. Which brings me to pointing out that this table shows the, for different modes of loading, so tensile, compression, shear, and bending, and then there's also a version of this for buckling and torsion. And then you have to start thinking about this in terms of different design regimes. Am I designing for stiffness? Am I designing for strength? Okay, and then you can use one of these constitutive laws to then help you pick a material that is lighter and stiffer and stronger. I'm sorry, pick the geometry that's lighter, stiffer, and stronger. Okay, so really important: modes of loading, design regime, constitutive laws. Now, so I've done this. I published this in a paper back in, what the heck was it, like 2000 or 2001, where I derived these equations, and then I started plugging in values, reasonable values for different materials. And I don't remember if these are the exact values I used in the, actually these are the same values I used in that paper. So this is a table that shows materials properties. And again, you could have designed these and made them better, but let's just take these for now because we're talking about geometry. And Steve, I can email this to you. Don't worry, you don't need to take a picture.
This is how I learn. I carry it around with me.
Okay, all right. So here we got different materials. We got carbon fiber, we got steel, we got magnesium, we got aluminum, fiberglass, titanium. These are different densities of these materials. With the carbon fiber, I think I'm assuming a 70% volume fraction. Carbon fiber and epoxy. These are the yield strengths of these materials. And these are the Young's moduli of these materials. And these are the Poisson's ratios, because we're going to need those later. It's worth noting here that this carbon fiber is not an anisotropic material. So this stiffness and this strength are only in one direction. And transverse to that one direction, they're going to be very different. Just keep that in mind. The metals here, well, not the fiberglass, the steel, the magnesium, the aluminum, the titanium, these are isotropic materials. Okay, if you, so some more notes here. What I assumed a AZ91 for the magnesium. I assumed a 6061 T6. So the T6 is the heat treatment. That's how it's been precipitation hardened. And for the titanium, I'm using a 6.4 titanium. So this is actually the pretty strong premium titanium. Okay. Now, if you go ahead and you plug in those materials values, and you can argue with me about those materials values, and you can go ahead and play with this and tweak them on your own if you're interested. But just using those as just a line in the sand, go ahead and plug those materials properties into these equations. You begin to see that you can then calculate out the potential weight savings at the same strength or the same stiffness at a given loading load, and see that the possibility, the potential to reduce weight for these different materials. So what's perhaps especially interesting here to me is that a lot of people talk about steel as an old-fashioned, not a good material to build racing bicycles out of, or racing cars or airplanes or whatever. Yet on a design for strength, on a design for stiffness, under tension compression, so linear loading, under the design for stiffness regime, steel you can actually make a lighter structure than these other materials, than magnesium, aluminum, titanium, and fiberglass. So most people would be surprised by this, because everyone talks about making aluminum cars and they're lighter and this and that, and they can be. We'll go into that later, but the main point here is that it doesn't always get you a lighter structure. If you have something that's only under tension or compression, or shear, and you're designing for stiffness, because steel is so stiff, you can actually end up with a lighter structure if you make it from steel. Okay, most people automatically go to aluminum or magnesium and think it's going to be a lighter structure, but not necessarily. The situation looks a lot different when you go into a more complicated loading like bending. When you start talking about bending, steel does horrible, right? Because the ratio of the stiffnesses is related to the 1/3 power, as you see right here. So all of a sudden, the advantage that steel has doesn't overcome its advantage or disadvantage in density. And then you start going down this list, and all of a sudden carbon fiber begins to make a lot of sense, because the potential for weight reduction compared to a steel with a 900 megapascal yield strength all of a sudden looks very good. You can have a small fraction of the weight if you make the structure out of carbon fiber and you're assuming the same strength and the same stiffness when you're in bending. So when I told you about remembering this, about the importance of internalizing the mode of loading, is it tension, is it bending, is it shear, is it buckling? This becomes really important when designing, because if you're only under tension, you might as well just use steel. You can probably make a lighter structure. And in some cases, you don't, when it's designed for stiffness and you're only under tension or compression, you can still do pretty good with steel. You can do better with steel than you can do with magnesium or aluminum. Okay, so I don't expect you guys to memorize these numbers or these equations, but just walk out of here knowing that steel is sometimes a good solution. It's not always a bad thing to make it out of steel. Sometimes you really can make a lighter structure out of steel than you can out of more, exotic materials, fancy magnesium alloys and aluminum and titanium and so forth. And then I've done the same thing here for torsion and buckling, and the situation looks very much the same. When you're under torsion or buckling, you really will struggle to do as well with steel as you could with some of these other materials. And then I split this up for solid members versus tubular members. And again, the story's about the same. You guys can go through and read this yourself when I distribute this, which I should do sooner rather than later. And you can figure out which of these materials make sense in each of these various applications. But it really does show you, like, carbon fiber, the properties that you can get out of carbon fiber when you're in a more complex loading situation like bending or tension, because it has such a high stiffness to density ratio and such a high strength to density ratio. It's amazing what you can do with carbon fiber. It is just amazing if you really optimize your use of carbon fiber.
Don, I have a
Yes,
question on that. So carbon fiber is good in tension, incredibly good in tension, but is it as good in shear and compression? I was under the impression it's so directional that it wouldn't be as good.
Right. So that's a really good point, because you have to make sure which direction of shear you're using, right? But you bring up a good point. You have to make sure in the case of shear you're going maybe perpendicular to the fibers. It's just a question of aligning the fibers for that particular load case. Good question.
So whereas with aluminum or steel, you might get you might get good properties for all of these different loading scenarios. For carbon fiber, you kind of just have to pick maybe one or two, right?
Right. So it's both a blessing and a curse, you know, anisotropy of carbon fiber. If your application, you know, if your design, if your structure, if you are very certain that of the loading conditions that it's going to live in its whole life, then you can go ahead and put the fibers in the direction of those loads and take advantage of their strength and stiffness. But if you have any off-axis loading, you could be in big trouble. You could be in big trouble, and this is a blessing and a curse. I mean, you're putting the mechanical capability only where you need it, which allows you to put it where to remove it from where you don't need it, and that's one thing that promotes the light weighting, taking advantage of that. But if things go wrong, you're in trouble. So here's a good example. Like, I've seen guys do this before. Like, you have a expensive carbon fiber bicycle frame, and when you're riding it, it's absolutely beautiful. It's stiff, it's light, it absorbs bumps. It has the feeling of lightweight of a good carbon fiber frame is just an absolute vision. It is such a huge difference. But you take that bike and you put it next to a lamp pole, and somehow you lose control, and the bike slams the top tube into the pole, and guess what? It'll go right through the top tube. I've seen it happen before. Then you're in trouble. Then you're, you know, it wasn't designed for that particular loading condition. And this is the thing with high performance carbon fiber bicycle frames is that if you're very, very careful with them, you can enjoy them for a long time. If you get sloppy with them and let them fall and hit other things or get into a crash when you're racing or something, they're probably going to fall apart, and they're not going to bend. They're just going to snap, and you're going to have little pieces all over the place, and you're going to have to basically junk the frame and buy a new frame. So, and it's the same thing for racing cars, like the Formula One. You know, Formula Ones are made out of monocoques. We'll talk about that later, but they're very directional. The monocoques are designed to be loaded in very specific ways. And if anything goes wrong and you get T-boned by another car, you're toast. You know, the thing fracture all over the place. So you know, it's really difficult to get isotropic properties out of using carbon fiber. And people have tried using cut up little fibers and mixing them together and having them in some random orientation and locking them in that direction, those directions with epoxy or polyester, whatever resin material. And those materials do approach isotropic behavior, but almost by definition, because they're getting to isotropic behavior, they no longer have the structural efficiency. So, for example, like there is a particular Italian bicycle parts manufacturer named Campagnolo that makes crank arms out of a random oriented carbon fiber mix. Okay, and those, yeah, they take loads in different directions and they don't fall apart. But ultimately, I'm not sure they're more structurally efficient than the really high quality, well-engineered aluminum parts. And they probably cost a lot more.
Question, Don.
Yeah.
You know, there's carbon fiber and carbon fiber. There's steel and steel. There's aluminum and there's aluminum. Have you do you know anyone who's ever analyzed the structural integrity and the other characteristics of each of these?
Sure. Let me show you some. That's a good segue to the next slide. Okay, so these are called, I think I've mentioned these before. These are called Ashby diagrams. And this is a graph of strength versus density. They also have graphs that are specific strength versus specific stiffness. The second one over here is stiffness or Young's modulus versus strength. They have these bubbles for different materials. Like here is a long skinny bubble for titanium. Okay, just like you asked, there's titanium and there's titanium. It's hard to see that, I recognize. And my cursor keeps disappearing. Right here. These are the titanium and the other titanium and the titanium before that. These are a variety of different titanium alloys compared on this, kind of imprecisely compared on this diagram. Okay, these lines right here are lines for different modes of loading. Okay, and the slope of these lines is given by this M value. In order to maximize the potential for structural efficiency, you want to maximize this M, so increase the slope. So you can look for materials at different slopes, different guidelines here, and then you can begin comparing different alloys within a given bubble. Okay. I have the Excel sheet that produces this somewhere. And if you were curious, Steve, you could go and start plugging in different values. You could look up 325 titanium. You could look up commercially pure titanium. You could look up 6.4 titanium, and you'll see that the strength changes. The stiffness doesn't change, or changes a tiny, tiny, tiny little bit, but the strength changes, and then you can start figuring out which of these materials make sense. But keep this in mind, that the stiffness isn't changing. So that means that the stiffness, for example, of a bicycle frame made from commercially pure titanium versus 6.4 titanium will be exactly the same. So if you have a titanium bicycle frame and you never plan on crashing and you just want a stiff frame, you'll get the same performance out of an inexpensive, well, relatively inexpensive commercially pure titanium frame as you would out of a 6.4 titanium frame. But the difference comes is when you crash or your bike hits a telephone pole by leaning in the wrong way, you need that strength to stop the top tube from denting, because you need that off-axis loading strength. Okay. Okay, I think that's it for today, guys. Yep, that's it for today. So next week we will start going into applying this to car body structures.
Can I ask one last question? Are these,
Sure.
on this slide here, the design for stiffness and strength, are they based upon some sort of computational formula for each, or where does the information come from?
So this information comes out of tables, I assume.
Okay.
So Professor Ashby, Michael Ashby, yeah, I think he's at Cambridge. I'm not sure if he's still alive or not. He back before the internet was really huge, there was all this talk in the materials community about creating good databases of materials properties. And there was all these different groups around the world that had different data, and it was all sort of stuck in their library, and nobody had access to all of it. So people were always scrambling around, calling each other, trying to find the value of different materials. And I think Michael Ashby saw this and said, well, we can plot all these out in these beautiful bubble diagrams. Okay, and this is a place where you can look and get a lot of information real quickly.
Yep.
Because I think he or his graduate students made the effort to collect the data from all these different databases around the world and put them together in order to, like I said, in order to make a concise, easy way of looking up all this information. He put them in these diagrams. And then again, these diagrams are very useful because then you can begin to understand, based on the slopes or based on the mode of loading and these lines and so forth and the M value, you can go ahead and figure out, what is the most structurally efficient option.
And for $50,000, you can buy a license to this program.
Wow. Got to make a lot of bicycles or automobiles for that.
Why would I do that? I bought a book for $17.95 that has most of this information in it. Anyway, I have Michael Ashby's book in the other room. But any other questions, guys?
Thank you, Don. Really interesting.
Glad you enjoyed it. We'll see you guys next week, and we'll talk
apologize.
about. Sorry, Steve. What?
I apologize, but I take this on the subway. I review your lectures on the. It's just my subway reading. That's how I learn this stuff. So.
Okay. Well, thank you. Thanks for reading. So again, next week we'll talk about applying the strategy to making lightweight car bodies.
Beautiful.
Okay. Have a good week, guys.
All right.
See you next
Thanks,
week.
Don.
Cheers.
See ya.